This is the first screencast for the homework that we have. I want to show you how I go about doing that, and you can decide how much you use it. Remember, I'm asking you to answer homework questions only on one side of your composition book, and then leave the other pages, the facing pages, blank. And those blank pages are for corrections to ones that you don't get correctly or would like to show more work for. Those corrections are going to allow you to get a curve on your test when we have them. The other thing to think about is even if you have the right answer in your initial work, if you don't show any work to get there or like a process to get there, that will not count as being fully corrected. So just as a heads up on that. All right, so I'm going to start off with problem 7. It says two identical metal charges, A and B, are in contact. Both are neutral. 1 times 10 to the 12th, which is, I believe, 1 trillion electrons are added to sphere A. Then the two spheres are separated. What's the charge of A and B after that? If they're identical spheres, they have identical shapes, volume, stuff like that. So the charge, the excess charge put on the left sphere would split evenly. So half the total, or 5 times 10 to the 11th electrons, would end up on each. If we want to put that in terms of Coulomb, I do the conversion from coulombs, from electrons to Coulomb. The charge on each electron is negative 1.6 times 10 to the negative 19th coulombs. So negative 8 times 10 to the negative 8th coulombs on each metal object. The next problem is problem 14, also pretty straightforward. This is a Coulomb, or Coulomb's law problem, and it ends up saying a small plastic sphere with a charge of negative 5 nanocoulombs is near another plastic sphere with a charge of negative 12 nanocoulombs if they repel each other and have a distant force of 8.2 times 10 to the negative 4th newtons. What's the distance between the spheres? So obviously these would have like charges, either both negative or both positive. That doesn't matter. So you have the force here. I have all this information in the numerator of Coulomb's law equation. I need to solve for R. So I basically take this, divide it by 8.2 times 10 to the negative 4th. That gets me R squared. Take the square root of that, and that gets me 2.57 centimeters. Or in standard units, which I prefer, 0.0257 meters. For problem 24, I'm going to check here, essentially saying a bumblebee can sense electric fields as they bend the hairs on its body. That's pretty cool. I mean, you can feel electric fields also if you're something like, you can feel your hair standing on end. So they can detect fields of 60 newtons per coulomb. Could a bumblebee use to do this? Yep. And if a bumblebee has a charge of 24 picocoulombs, how far away could another bumblebee detect that? We would need to know that picocoulombs is 1 times 10 to the negative 12th. So pico is 1 times 10 to the negative 12th. And here I'm looking at the prefixes on your formula sheet. And there's pico that lets you know what that is and lets you know mathematically what that is. So if you're unsure, go ahead and refer back to that formula sheet. So because the B would act as a point source, I'm going to use this formula, which is, I believe, formula E3 on your formula sheet. By the way, when you get them on the AP exam, they're not going to be labeled with the A, like the E's and the things like that. That's my doing. So that's KQ over R squared. I rearrange to solve for R squared. I get 0.0036 meters squared, really, should be here, is equal to R squared. So that radius is 0.06 meters, 6 centimeters. I don't know if that's that useful. I mean, I would think the bees could see other bees that far away, but you never know. They can also use this, by the way, I think it said in the chapter, to detect which flowers have been recently pollinated. So that is useful, so they don't waste their time going to a flower where the nectar's already been just taken. Problem 29 is a vector problem, and so it has two identical 1 nanocoulomb spheres or point sources. They're 10 centimeters away from each other total. And then at the midpoint, 5 centimeters to the right, there's a point in space. And it's asking you what the electric field is, both direction and magnitude at that spot. So there's quite a bit to this one. This took me a whole page to do. If it's taking you 2 lines to do, you're probably not putting in all the effort you need to. You're probably not thinking about it quite right. So I want to use symmetry. So because this point is equidistant from the top charge and the bottom charge, and if I look where it is, I could tell that the electric field from this top charge would point down and to the right. The electric field from the bottom charge would point up and to the right. So the vertical fields would actually cancel out. The horizontal fields will add up. So what I'm going to do first is just find the electric field at this point, caused by one of the charges. So I think I call this charge 1 and charge 2. So first of all, we've got to find this distance because it's not 5 centimeters away. So that's Pythagorean theorem. That gets me 7.1 centimeters away, or 0.071 meters. So then the electric field at this point caused by this charge, using formula E3 up here, 1785 newtons per coulomb. So that's caused by each of the 1 nanocoulomb charges. And this shows you how the symmetry, where the up part and the down part, or the vertical parts, I guess, cancel out, and our net field is pointing to the right. So what I can do is I can figure out the horizontal component of this 1785 newtons per coulomb that's produced by one of the charges, and add the horizontal component, and add that up to the other horizontal component. So I get this, cosine of 45 degrees is around 1260 newtons per coulomb. And so then when I take that horizontal component and multiply it by both charges, I get around 2520 newtons per coulomb to the right. So again, if you need to, take a minute and make sure you go back and look through those. For problem 33, it says a parallel plate capacitor is formed from two 4x4 centimeter electrodes spaced 2 millimeters apart. I talked about this formula the other day. It's this electric field is epsilon sub 0 times charge divided by area. And it's the area of any one of the plates. And this is formula E9 on our formula sheet. So when I do that, I draw it out. I know the electric field strength. To get the area, if each side is 4 centimeters, then that's 0.0016 meters squared, I guess. And then I'm rearranging that. So to solve for Q, pardon me, I think I said the formula wrong to begin with. It's Q over vacuum, I think it's permeability. Let me just check that. Permittivity. There's another constant later we'll see. So that's vacuum permittivity times the area. So just rearranging that, solving for Q, I get 1.4 times 10 to the negative 8th coulombs. It's around 14 nanocoulombs. I don't remember if they asked it for it. Oh, yep, they did ask for it in nanocoulombs. So I do it in standard units first and then convert. 35 is similar to 33, and then we're going to use this formula down here again. It's formula 9. So you want to find the charge on this. The big idea behind this is it's a 1 gram plastic bead. It tells you the charge on it. So if it's hovering in between these two plates, that says we've got balanced forces. We know gravitational force acts down, therefore the electric force should act up. And therefore now, if I can use the mass to find the gravitational force, so mg, 1 times 10 to the negative 3rd kilograms, because we want standard units, times 9.8 newtons per kilogram gives me 0.0098 newtons. So therefore the electric force up also has to be 0.0098 newtons. So if that's true, now I'm going to use my general formula for electric field to find electric field strength, 1.63 times 10 to the 6 newtons per coulomb, and I'm going to use that field strength to end up finding the charge on each plate. So Q is something that I'm looking for. I know E. I know vacuum permittivity is because it's a constant. The area of the plate, well, they gave me this as a 12 centimeter diameter. So the area of a circle is pi r squared, but r is half of this, and it should be in meters. So pi times 0.06 meters squared, so that's my area. So I rearrange this in order to get the charge. That's the charge on each plate. That was part B. Part A was easy. I forgot about it, so I did it at the end. So the electric force on the negative charge must be up. So therefore the top plate has to be positively charged, the bottom plate has to be negatively charged. 37 and 51. I think I have a good diagram for 37. So basically it's asking you to fill in what the charges would look like down here on this lump. So the charges would pile up toward the top. The electric field is going to be strongest where the charges are piled the most. I'm betting that this would cause the charges up here in the cloud, the negatives, to pile up there as well at that point. So essentially with less distance in between, polarization allows these charges to be pulled up. these excess positives to be pulled up, and therefore there's a stronger electric field in here since there's more charges. And the lightning is likely to strike at that point, so stay away from a tall tree or a tall hill when there's a lightning storm. Problem 51 is the last one. That's saying two equally charged 1 gram spheres are placed with 2 centimeters between their centers, and the initial, when released, the initial acceleration is 225 meters per second squared. What's the magnitude of the charge on each sphere? So overall, I've got this force over mass. So I know the mass of the charges, I know the acceleration of the charges. So using Newton's second law, I can find out the net force on those charges. So now I'm going to go back. I'm going to say if that's the force between the charges, and then I know the distance between them, I can use a version of Coulomb's law to figure out the charge on each one. So I find that, and this is similar to the last problem you did on your lab, where you're doing that, to figure out the charge on each piece of tape. So this ends up being 1 times 10 to the negative 7th coulombs. I believe that's 100 nanocoulombs or 0.1 microcoulombs. You might be thinking, well, wait a minute, if we're asking about thinking about the net force on these things, would we have to consider gravity like in that acceleration? And you really don't, because if you look at the gravitational force formula, which is this over here, and we know the mass of each object and the distance is still the same, we can figure out that the gravitational force of attraction is going to be 1.67 times 10 to the negative 13th newtons. Well, this is 0.225 newtons. So this is ridiculously small, meaning it is meaningless, and we can ignore that. So I just wanted to make sure I showed that to you so you could think about the difference in magnitudes between electric forces and gravitational forces. I hope this helps, and if you have other questions on homework, hopefully we'll go over them in class. Thanks.